Hello friends, welcome back to Scientific Blunders, where we learn the don'ts first. Today we're going to start a new series on probability, and although this is a very ancient science, I think this has become particularly relevant in today's day and age of computers, where we are heavily relying on the concepts from probability and statistics to make decisions under uncertainty, especially in applications in artificial intelligence and computer vision and machine learning and so on. So this is a very, very important topic, especially in today's modern age of computers. So here's the problem. Let x be a random variable with a uniform distribution from -half to half. If y equals x squared, calculate the covariance of x and y to check if they're independent. Alright, so let me create some space here. There we go. And so we have the distribution of x. So x has a fairly simple distribution, a fairly standard distribution. So this is the random variable x on the x-axis, and this is the probability density of x, what we can call f of x on the y-axis. It's the probability density of the random variable x taking the value small x, and x takes values from -half to half, and because it's a uniform distribution, the probability density is the same everywhere, and we know that the area under the distribution has to be 1, which means the value of f of x would be 1 for all values of x. Fair enough. And now we want to calculate the covariance of x and y to check if they are independent. Right? So by just a quick refresher on what covariance is, the definition of covariance is that it's the expected value of x minus the expected value of x, or the mean of x, times y minus the expected value of y, or the mean of y. And if we were to simplify this, we would get that the covariance equals the expected value of xy minus the expected value of x times the expected value of y. So a fairly nice expression for the covariance of xy. And so we know what y is. Y is the square of x. So we could simplify this to the expected value of x times the square of x. So that's the cube of x cube, minus the expectation of x times the expectation of x squared. Right? So we have the distribution of x. As of now, we don't know the distribution of x squared or the distribution of x cube. But let's calculate the expected value of x, just so that we can plug that in here and simplify the equation a little bit. So the expected value of x, by definition of expected value, is the weighted average of x. That's how I like to think about it. So it's x times the weight, and the weight is the probability in this case, integrated over all values of x. And luckily f of x is just 1, which makes the math very easy, and x varies from -half to half. And because x is an odd function, this integral is going to evaluate to 0. And we could have said that just by looking at the distribution, in that it's symmetrical about both sides of the y-axis. So the average value is going to be the midpoint, which is 0. Right? So that is great, because now we can substitute this entire term, because expectation of x is 0, this entire term is going to go to 0. Awesome, we have really simplified the expression quite a bit. So all we have to do is now calculate the expectation of x cubed. So how do we do that? Let's see. We know that if x varies from -half to half, x cubed, let me write that down. If x varies from -half to half, so the integral of f of x dx from -half to half, right, which is the area under this distribution, which is 1, that has to equal the area under the new distribution, which has to equal 1. And let's say the new distribution of x cube, let's call that g of x. G of x dx, and or maybe I should use a different variable just so that it's not ambiguous. So let's say the new variable is, let's call that z. Let's say z equals x cube. Right, now we want to find the distribution of z, and let's say the distribution of z is g of z. Right, let me write that down as well. So the distribution of z, probability density of z taking the value small z, we are going to call that g of z, and that's what we want to find so that we can calculate the expected value of z. Right, so let me scroll down a little bit. And if x takes the value minus half, z will take the value minus 1 by 8, and if x takes the value half, z will take the value 1 by 8. Right, so this has to equal 1 because these are both probability distributions. Right, so how do we know the expression for f of x? F of x is just 1. Right, so we want to obtain the expression for g of z. Right, so to do that, let's use the fact that z equals x cube, which we already have used here, but let's use that over here as well. So if z equals x cube, dz would be 3x squared dx. Right, or that would mean dx equals dz by 3x squared. And if z equals x cube, we can say that x equals z to the 1/3. Right, so that means dx would be dz by 3x squared, so 3z to the power 2/3. Okay, that's great. So now we have x in terms of z, and we also have dx in terms of dz. And so that means, so we have basically said that we can replace x with z, right? So f of the cube root of z, and we can replace dx with what we computed here. And now, since we have changed the variable from x to z, we can also change the limits of the integral appropriately. So if x is minus 1/2, z would be minus 1/8. And when x is half, z would be 1/8. And so that would equal the right hand side of the equation that we have here. So minus 1 by 8 to 1 by 8, g of z dz. Okay, awesome. So now we had two variables x and z. We have somehow simplified that to just one variable. And so now we have two sides of an equation. They're both integrals. They have the same limits and the same variables. So that should mean that the term that we're integrating, or what is formally called the integrand, those should also be the same, right? So that means f of z to the power of 1 by 3 divided by 3z to the power of 2 by 3, that should equal g of z, right? We're almost there. F of z to the power of 1 by 3, right? So the way we had defined f, it was 1 everywhere for these values of x, and so x maps to a different x ranging from minus half to half maps to z ranging from minus 1/8 to 1/8. So that would mean that it would still be 1 everywhere, right? So this would still be 1 for all values of z that we are interested in, which is this range of z. So that is great. And g of z And we're done. We have computed the value, we have computed the distribution of the random variable z. Right? And remember, z was x cube. So we have computed the distribution of x cube. What we wanted to do here was to calculate its expectation. And some of you may have already guessed a much better way to do this, but I just wanted to walk through the math just so that it's clearer and more convincing this way. To compute the expected value of g of z, all we have to do is again use the definition of the expected value, which is the weighted average, which is how I like to think about it. So g of z, or let me say, it's the weighted average of z using g of z as the weights, and this goes from minus 1/8 to 1/8, and now g of z is what we have here. So this would be, let's see, we have a 1/3 from here. We have z divided by z to the power of 2/3 dz. Alright, so if you were to evaluate this integral, you would get 0. And similar to the reasoning that we had earlier, that z, the cube root of z is symmetrical about, it's an odd function, so it's symmetrical about both sides of the y-axis. So this integral would evaluate to 0. So this term also evaluates to 0. Isn't that interesting? So the covariance of xy is 0. Now this is a fairly standard problem, and the purpose of this YouTube channel is not really to solve problems. I think there are plenty of great resources out there to do that. But I think there's an important lesson to be learned here, which is really the motto of this channel, to learn, to clear some of the misconceptions that we have. The covariance of two random variables is 0, but are they independent? We have x, which is here, and y, I told you that y was equal to x squared, which means y clearly depends on x, right? And yet their covariance is 0. So what does that mean? So that means, and this is probably the key takeaway from this video, that if two random variables are independent, then the expectation of xy would equal the expectation of x times the expectation of y, and that means that covariance would be 0. So this is something we can say for sure. Whereas if the covariance of two random variables is 0, like we have here, right? We have random variable x and we have a random variable y, which is the square of x, and they have a 0 covariance, which I think is really interesting. Yet we cannot conclude that they are independent. So just to reiterate, if two random variables are independent, they will have 0 covariance for sure. Whereas if two random variables have 0 covariance, they may or may not be independent. So this statement doesn't hold true both ways. So we have to be really careful when we're making conclusions using the covariance. And that, my friends, is the key lesson to be learned from this video. See you soon.